Going back to section 3.2, we have a problem if only one sample is taken in practice. Based on the picture that's here, we have our initial sample, the one that's sort of a peach color, that gives us the point estimate, but we have all those blue samples that give us the sampling distribution, and we need the sampling distribution in order to get the standard error. If we can't get that, it looks like this whole thing falls apart, because if we have no standard error, how do we compute a margin of error, and then how do we get the endpoints for a confidence interval? So we've got a problem, but there is a workaround for this, which is something called bootstrapping. And bootstrapping is a procedure that we can use to simulate a sampling distribution when we don't have all of the blue samples, when we just have this single peach-colored sample. This is a lot easier to explain using a sample, especially a quantitative sample, so that's what we're going to start with. We've got our sample of 20 randomly selected garbage weights, and we know what the sample mean is of that sample. That's 30.8. That's going to be our point estimate, but whatever this bootstrapping procedure is, we're going to apply it to this sample. Really what we end up doing is we end up using our sample to create a proxy for the population, where our proxy is lots and lots of copies of that original sample. This idea is only going to make sense if the sample is representative of the population. If it's not, you're going to end up with a proxy population that's nothing like the real population, so you're going to end up with a very distorted confidence interval ultimately. But if you have a representative sample, this is a reasonable thing to do. And more specifically, the way that we've talked about it so far, if you have a randomly selected sample, that'll represent the population appropriately, and that'll work. In order to do this properly, we would really need infinitely many copies of the sample, not 12, but this picture here is supposed to illustrate the idea, where the numbers that are in bold in the upper left are the initial sample, and then essentially I just copied that 11 times. So you'd have a lot more than 12 copies of the original sample, and then what you'd have to do is take random samples of size 20. So you want your samples to be of the same size as the original sample from that proxy population. We're still going to have a slight problem, but it's easy to work around it. And it's right there on the previous slide, the idea of having infinitely many copies. You'd never finish making all of the copies, so then when would you actually be able to take the sample? Well, you wouldn't, but there's an equivalent procedure that we can do where you don't have to make infinitely many copies. That equivalent procedure is sampling with replacement from that one sample. Essentially what you do is you have your initial sample, and you're going to sample with replacement until you have a new sample that's the same size as the original. So with the garbage weights, you would sample repeatedly with replacement from the original sample so that you have a sample of size 20. To illustrate the idea of sampling with replacement, I thought it would be easier with pictures. So we've got some corporate logos here. We have 8 S&P 500 companies, and suppose you want to estimate something numeric. I guess you can pick whatever you want. I picked average price to book ratio. But we have our 8 companies here, and let's say we're going to take bootstrap samples. So they're going to be the same size. They're going to be size 8, and we're going to take samples with replacement, which means that we're going to get duplicates. That looks wrong intuitively, but that's actually the thing that makes this work. If there weren't duplicates, we would just keep getting the same sample over and over and over again. By sampling with replacement, yes, that means that in some bootstrap samples you're going to have elements that repeat and other ones that are left out. That's fine, and that's what's supposed to happen, because when that happens, that's how you get a distribution of values. Not only is it supposed to happen, without it, this wouldn't work. You wouldn't really get anything useful. To take a bootstrap sample, this is what you need to do. It's sampling with replacement from the original sample, using the same sample size, whatever that is. With the corporate logos, it's 8. With the garbage weights, it's 20. Sticking with the corporate logos for now, here's one possible bootstrap sample. There are some repeats. Floor is in there twice. Public storage is in there twice, which means that there are a couple missing. It looks like IBM isn't there, and it looks like Allstate isn't there. That's fine. There's nothing wrong with that. Looking at this bootstrap sample, it's the same size as the original, right? Size 8. And it's done with replacement, which is why there are duplicates in here. Here's another possible bootstrap sample. Again, we have some duplicates. There are 3 nye sources in it this time. That's okay. There's no max on how many repeats you could have. In theory, you could have a bootstrap sample consisting of 8 nye sources. That would be an unlikely scenario. The chance of that happening, I suppose, would be 1/8 raised to the 8th power. But it is possible. It's okay to have individual bootstrap samples that look a little weird in terms of the number of repetitions. That's completely fine. But again, size 8, done with replacement. Here's the same idea applied to the garbage weight example. We have the original sample first, then a couple of bootstrap samples. The bootstrap samples are going to contain different repeated elements and different left out elements, which is going to cause the sample mean to shift. Notice that you don't get 30.8 every time, which is perfectly fine. That first bootstrap sample, you get something fairly close, 30.75. That's pretty close to 30.8. The second one, you get something that's a little bit bigger. There's certainly nothing wrong with that happening. For some general definitions, the way that you take a bootstrap sample, it's a random sample taken with replacement from the original sample with the same size. In the case of the corporate logos, size 8. In the case of the garbage samples, size 20. Same size as the original sample in general. From each bootstrap sample, you'd be able to compute a bootstrap statistic. Those weren't visible with the corporate logos. We didn't have the price to book ratios, but they were with the garbage weights because we had the different sample means for the bootstrap samples. Those are bootstrap statistics. So the 30.75 is a bootstrap statistic, so is the 31.3. And then if you have a whole bunch of bootstrap samples, so rather than just a couple, what if you had a couple thousand or a few thousand? And for each one you computed a bootstrap statistic, then a bootstrap distribution would be the distribution of all of those bootstrap statistics that you have. And that's the thing that you can use to get a proxy value for the standard error. This is the sort of thing that you end up with, where the most important number on this screen is right here. It's the 2.482, the thing that's listed as standard error inside of the picture, because that's the standard deviation of what's in that picture, and what's in that picture is the bootstrap distribution. So that's really the key point here, is that we can use the standard deviation of the bootstrap distribution as an estimate of the standard error, and then that's how we can get a confidence interval. Even though it will repeat in the how-to stat key video for constructing bootstrap confidence intervals, I figured it was worth showing how you get this screen. In stat key, everything that you want for sections 3.3 and 3.4 is in this column right here, underneath where it says bootstrap confidence intervals. We're not going to do anything with the slope or correlation because that's in chapter 2. We haven't talked about that yet. All of the regression and slope stuff will be at the end of the course. But these first 4 options, so for a single mean, we're going to need that. That's actually what you use for the garbage weights. Single proportion, we'll use that a little bit later. Difference of means, difference of proportions, those will just be in the how-to stat key video, not in this one. But for the garbage weights, that's estimating a single mean, so you want this option right here. And there is a default data set that's preloaded. We need to get rid of that and replace it with the garbage weights. So edit data, delete all this stuff. I'm going to uncheck data has header row because I have the numbers in this text file right here. That way I don't have to retype them. So I'm just going to copy them over. And now they're in there. There's the sample mean right there of 30.8. So I've got all the numbers in there correctly. Then generally you want to have at least 5,000 bootstrap samples. In practice, the standard is usually 10,000. And if we were using R or STA or SAS, then I think I would require that. But with stat key, it seems like it starts to strain after you get above about 5,000 or 6,000. So that's why in lab 3 it says at least 5,000, by which I mean you can just stop at 5,000 if you want, because past that it does start to strain a bit. The way to do it is this button right here. That's how you get there fast. I guess you could do it by hundreds or tens if you wanted to, but if I just click on this 5 times, there's 5,000 bootstrap samples. And if I turn the presentation mode on, it'll make those numbers a little bigger. I'm getting something slightly different. Here I'm getting 2.484 instead of the 2.482 that's in the notes for the standard deviation of the bootstrap distribution. That's okay. I'm randomly generating a bootstrap distribution. Since there's that random element, you're not going to get the same thing every time. It might be slightly different, and this is really a slight difference. It's off by 0.02. That's not much. In any event, that is the part that you want. Other than that, the only other thing that you're going to need for a confidence interval, which we're going to need a little bit later, is just the 30.8, because that's the mean of the original sample. That's your X bar. And what's up here, the X bar, the mean of your original sample, it doesn't have to match this. And notice that it doesn't. The 30.813, it's a little bit bigger than 30.8. It's okay that that's a little bit different. That's just due to randomness because the bootstrap samples are randomly generated. There's a slight difference there, but that's nothing to be worried about. Generally, the sampling distribution will be centered around the population parameter. In a similar sense, the bootstrap distribution that you construct will be centered around the original sample statistic. Since there is a random element to the generation of bootstrap samples, it may not be perfectly centered, which we just saw. With the garbage, you don't get exactly 30.8. We had 30.813. Or if I go back for a second, the one that I have in the slides doesn't have 30.8 either. It has 30.793. Still very close, and that slight difference is really just due to the fact that the bootstrap samples are randomly generated. It's nothing to worry about. It's nothing that's wrong. The important part is down below, the variability. The variability of bootstrap statistics will be similar to the variability of sample statistics, which would mean that the standard deviation of a bootstrap distribution should be similar to the standard deviation of a sampling distribution, and that's why we can use it as an estimate. And this is the biggest point in this section right there. It's that last point on this slide that the standard error of a statistic can be estimated using the standard deviation of the bootstrap distribution. This is how we fix that problem that's in the first slide in this section. We can use the standard deviation of the bootstrap distribution as an estimate, and then, since we have an estimate for the standard error, we'll be able to compute a confidence interval. So here is an updated picture of what really happens. We have our initial sample. Notice the population is nowhere now because we don't have data from everybody in the population. This is really what we've got. We've got our original sample, which will give us the point estimate, the statistic, whether that's an X bar or P hat, difference of X bars, difference of P hats, whatever it happens to be. From our original sample, we can generate a whole bunch of bootstrap samples of the same size with replacement. From there, we can get a bootstrap distribution. The standard deviation of that we can use as a point estimate for the standard error, and then we have a way to compute the margin of error, so therefore we have a way to get endpoints of the interval. Going back to the garbage weight example, we know that the mean of the original sample is 30.8 pounds. Using the screenshot that I have in the notes, the standard deviation of the bootstrap distribution was 2.482 pounds. If we're going to use the standard deviation of the bootstrap distribution as a point estimate for the standard error, we can go ahead and get that interval. For a 95% confidence interval, that's where we can compute the margin of error as 2 times the standard error. So at this point, it's just substituting in and simplifying. Say, okay, 30.8 is our point estimate, 2.482 is the standard error, and then it's a couple of algebraic steps and we're done. The most important thing right now is getting the X bar and the standard error estimate correct. It's easy to get those wrong, to be pulling them from the wrong spots in the stat key output. The standard error estimate, the standard deviation of the bootstrap distribution, that is in the picture. It's in the upper right corner of the picture where it says standard error. If you go back a few slides, that's where the 2.482 is. The X bar, the point estimate, is not inside the picture. It's in the original sample box. I guess really it's above the original sample box, but it's underneath the original sample heading. The common mistake is to pull both of those estimates out of the same place. Either to pull them both out of the picture or to pull them both out of the original sample box. But you don't want to do either of those things. It's one of each. The point estimate, in this case X bar, comes from the original sample box, but then the estimate for the standard error comes from inside the picture. because what's inside the picture relates to that distribution that's being graphed, and that's the bootstrap distribution, so that's where the standard deviation of the bootstrap distribution is. Then we want to give an interpretation of the confidence interval. The hard thing is getting the parameter, so the same three things that we needed before in section 3.2. We need the type and number. It's a mean, not a proportion. Generally, if you have quantitative data, which we have here, right, the garbage measurements, they're numbers. They're not categories, they're not just words. You do get numerical values. If you have numerical values, typically it is a mean. The population would be all households, since the sample was just 20 households. And if the sample is supposed to be a little piece of the population, it seems like the population should be all households. And then the specification part, which is a lot of wording this time, the weight of garbage discarded during the previous week. The three things that we need for the parameter are in there. And now that we have the parameter, getting the interpretation of the interval is basically you can take the parameter, put the confidence level in front, put the interval endpoints at the end. You get something like this, that we're 95% confident that the parameter, the mean weight of garbage discarded by all households during the previous week, is between the endpoints of the interval, 25.836 pounds and 35.764 pounds. In general, if you take more bootstrap samples, you'll get a better estimate of the standard error. However, there are diminishing returns on that. Certainly if you only had 20 or 50 or 100 bootstrap samples and then you jumped up to a few thousand, that few thousand will give you a better estimate of the standard error than 50 would. That's certainly true. But once you get past a few thousand, yes, you're going to get a better estimate if you keep adding more bootstrap samples in, but the effect eventually becomes negligible. So past a few thousand, you don't really get a whole lot extra if you keep going. And the usual standard is 10,000. That's typically what it is in practice. But like I said earlier, StatKey starts to strain a bit if you go above 5,000. So we're going to cap it at 5,000 for now. Here we have the poll data from one of the polls that carried forward from section 3.1 to section 3.2, the Marist one, where out of 873 registered voters, 454 said that they would rather elect the president via popular vote. We can get the sample proportion, 454 divided by 873, and that'll be enough to generate a bootstrap distribution. To generate a bootstrap distribution for this data, this isn't quantitative data, it's categorical data. The individual values aren't numbers, they're popular vote, electoral college, and I don't know. Those aren't numbers, but those are the possible responses here. So this is categorical data. That's typically where you would use a proportion, and that's what we're going to do here. I'd already done this in StatKey and put the screenshot in here. All you have to specify in the original sample is the numerator and denominator, and then it's clicking on generate 1,000 samples 5 times, and you have your bootstrap distribution. I think this is also worth going through, even though it's in the StatKey how-to video. Here, this should be a confidence interval for a single proportion. That's what we're trying to estimate. And it was 454 out of 873. So if I go to edit data, because again, we have our original sample box over here that has a preloaded sample proportion that we don't need. So we got to change this to 454 divided by 873. The 873 is the sample size. Count really means the number of successes in a sense, where a success is just whatever outcome you're interested in. Here, the one that we're emphasizing is preferring to decide a presidential election via popular vote. So that was 454 people who said that out of 873. So that's the numerator, essentially. The count would just be the numerator. And then sample size 873. Okay. Generate 5,000 samples. And there you go. If we're going to get the confidence interval, we would need our initial sample proportion, which is right here, the 0.52. I know here it happens to match exactly. It's a 0.52 right there as well. But really it's this. And then the estimate for the standard error is right there, the 0.017. So those are the two pieces that we're going to need. What I've got here matches exactly. So I suppose then the work would be identical for the one that I have in the slides and the one that I just generated using StatKey. So we want to get a 95% confidence interval for P. Well, we have P hat. We have the estimate of the standard error. That shouldn't be too bad. Substituting in, we've got 0.52 for p hat and 0.017 for the standard deviation of the bootstrap distribution, which is our estimate of the standard error. Couple of algebraic steps, multiply and then do the plus minus, and we've got our endpoints. And then giving an interpretation at the interval. So 95% confident at the beginning, endpoints at the end, and in between we need our parameter. The type of number is a proportion this time, not a mean. And generally that's the way it works with categorical variables. Typically there you're dealing with proportions, not means, because you can't average non-numeric values. So that's essentially why, because the idea of computing a mean is not really an option when you don't have numbers. So here this will be a proportion. The population would be all registered voters, and the specification part would be preferring to elect the president via popular vote. Putting all that together, our parameter is the proportion of all registered voters who would prefer the president to be elected via popular vote. And there's our interpretation. The last part, can we conclude that p is likely greater than 0.5? Well, the sample proportion is, because the sample proportion is 0.52. However, for a question like this, you want to make sure you use the interval to answer the question, and you need the whole interval to be greater than 0.5, and it's not, because the lower endpoint is 0.486. So the correct answer to that question is no, because part of the confidence interval is below 0.5.